Hi, this is Alex from devstories.eu. Biopython Fundamentals, Episode 9 of 18. Writing regular expressions to scrape plain text output files is a bioinformatic rite of passage. It is also an anti-pattern. The moment a search tool updates its visual formatting, your script breaks. To get structural guarantees, you need to rely on structured data. This episode covers parsing natively, unpacking BLAST XML. Biopython handles this using the NCBI XML module within the bio.blast package. Instead of saving your search results as a human-readable text block, you save them as an XML file. When you open this file and pass the handle to the parse function in the NCBI XML module, it does not load a massive text blob into memory. Instead, it returns an iterator. This iterator yields structured objects one at a time, keeping your memory footprint low even if your search returned massive amounts of data. To use this efficiently, you must understand the three-level hierarchy Biopython uses to model the results. The top level is the BLAST record. One record corresponds to exactly one sequence you submitted as a query. If you submitted a single sequence, the iterator yields one record. If you submitted 50 sequences, it yields 50 records. Inside each BLAST record, you will find a list of alignments. An alignment represents a single database hit. It tells you that a specific sequence in the database matched your query, along with metadata about that database entry. Inside each alignment is the third level, high-scoring segment pairs, universally known as HSPs. This is the part that matters. An alignment simply indicates that two sequences are related. The HSP contains the mathematical and structural proof of that relationship. A single alignment can contain multiple HSPs if the sequences share multiple distinct regions of similarity separated by unaligned gaps. Extracting the data means writing three nested loops. First, you iterate over the records in the parsed XML. Second, you iterate over the alignments inside each record. Third, you iterate over the HSPs inside each alignment. Once you are inside that innermost loop, you have access to the actual match data. This is where you apply your statistical filters. The most common filter is the e-value, which represents the number of hits of similar quality you would expect to see by chance. You access this via the expect attribute on the HSP object. You write a conditional check. If the HSP.expect is less than your threshold, say 0.04, you process the match. If it is higher, the match is too weak and you ignore it. For the hits that pass your filter, the HSP object holds the exact alignment strings. The query attribute contains your input sequence with any gaps introduced by the algorithm. The SBJCat attribute contains the matched database sequence. The match attribute sits conceptually between them, mapping out the exact matches, positive substitutions, or gaps. The real advantage here is stability. By letting the NCBI XML module unpack the file, you stop relying on brittle text scraping and start interacting with defined data objects that map perfectly to the biological reality of records, alignments, and segment pairs. Thanks for listening. Happy coding, everyone!